talk about the laws of thermodynamics. Okay, so the law of conservation of matter says whenever matter undergoes a physical or chemical change, no atoms are created or destroyed. So we can change, like we can take that uranium and we can break it up into smaller things, but we're never going to get rid of that atom. Okay, that atom cannot be created and it cannot be destroyed. It's just going to maybe change forms. It's going to be in different ways, like all that kind of stuff. So next, now we're getting into stuff that I haven't talked about, and that's energy. So when we are talking about ecology, energy probably is the most important thing in ecology, because energy is how we are all alive, right? Plants are going to get their energy from the sun. We're going to get our energy from plants, or other animals are going to get their energy from plants. That energy is then going to be transferred to us when we eat the animal. So when we're talking about energy, it's extremely important that we talk about energy both in the bios, like in the biosphere, as far as energy transfer within an ecosystem, but we also talk about our energy needs. How again do we keep the lights on? How do we move cars? All of that good stuff. Okay, so let's you guys should have already kind of talked about these types of energy. We have kinetic energy, which is basically energy of motion. Energy of motion. So we can actually get energy from the motion of flowing water. That's what dams are. Dams are actually places where water runs through, and the energy from the water is transferred, and we use it to power our homes. Wind energy. So we take the wind is going to turn the turbines, and that's going to create energy. And heat. Heat is transferred by radiation, which is basically exactly what it sounds like. Anytime you radiate something out, it's coming off. So radiation is heat that's coming off of something. Like when you, for instance, drive your car, right? When you get out, you can touch the hood and it's hot. That's radiation heat. It has radiated out of the engine and onto the hood of the car. That's radiation heat. Conduction is like it flow, anytime you conduct anything, you're flowing something through. Okay, so we can conduct heat. When we use it in our homes, we conduct heat all throughout our homes, right? We turn the thermostat on, the heat comes on, and we conduct that through our homes. Convection is like a circular form of moving heat around, sort of in a circle. And we'll talk more about that later when we talk about biomes and all of that stuff. All right, electromagnetic radiation is another form of kinetic energy. So essentially, electromagnetic radiation is going to give us X-rays, UV rays. X-rays are what, if you have to go get, if you think you might have broken a bone, you may go get an X-ray. UV radiation, microwaves that we cook our food with, all of these are types of kinetic energy that are electromagnetic. Okay. Potential energy is stored energy. So if we're looking at a dam, we are getting the energy from the water, from the flowing water as it goes over the dam. But if we hold the water here, so what a dam does is it's going to hold the water on this side. Okay, it's holding the water. And then it has these little, hold on, let me get my drawing utensil out so I can show you. So then right here, it's going to have these little, it's going to have these little like gates. Okay. So when energy is needed, the gates are going to go up and water is going to start to flow down. So right now, as the water sits in this river or lake, this is potential energy. Okay. Potential. When they open the gates and it flows out, this is kinetic. So we turn this energy into energy of motion. But first, we're going to hold it here. Okay. In chemicals, if we're talking about chemical energy, we store energy in bonds, in chemical bonds. And I promise, I will ask this question on a test. We store energy in chemicals in their bonds. Okay? So for chemicals, it's in their bonds, but for water, it's in their motion or lack thereof. We're stopping the water here and keeping it motionless, and then we are allowing the water to go through. So if you think of you and you're standing on top of a cliff, you have a significant amount of potential energy. You're just standing here, but if you fall off the cliff, hopefully onto like, marshmallows or pillows or something really fluffy down here. If you fall off the cliff, this is kinetic energy. So it's potential while you're at the top, but not moving. And it's kinetic as you're moving, as you're falling. Okay. Energy comes in many forms. So the sun provides most of the energy. Okay, so the sun is going to provide most of the energy that is in any ecosystem. In fact, the sun provides all of it in an ecosystem. So the sun is going to help the plants grow, and the plants are going to basically give energy to everywhere else. Okay, it warms the earth. It obviously has plant photosynthesis. The sun's energy is also what creates wind. The biomass is something we're going to talk a lot about. Biomass is basically the mass of all of the living things in an ecosystem. And so we're going to talk about that a lot. And then fossil fuels provide us energy, coal, natural gas, all of that. Those are also energy forms that we use. So I guess the winds are somewhat controlled by the sun, but hydropower, biomass, and fossil fuels aren't really controlled by the sun, except for the biomass. Photosynthesis creates the original biomass, so you could go about it that way. So, like, in other words, plants create sugar, then they are part of the biomass that we can use for energy. And again, we're going to talk a lot about biomass in future. All right, some useful types of energy. So just like we had useful mass, we also now are going to have useful energy. So useful energy has a high capacity to do work because the definition of energy is the capacity to do work. And high quality energy is going to have a high capacity to do work. It's going to be concentrated. Usually it's high temperature heat or strong winds or fossil fuels. All of these are considered high energy compounds or high quality energy. Low quality energy, again, is disbursement. So if I'm looking at like this picture, okay, the sun is obviously high quality energy, right? But the sun has transferred its energy and has heated up the water in the ocean. But because it's not concentrated, it's dispersed throughout this giant ocean. That makes the energy that moves from the sun to the ocean to be low quality, right? Because it is so dispersed throughout all of this liquid that there's no way to harness the heat energy in water. Now, you can harness the energy in the kinetic energy of water, in the movement of water. But if you took all of the heat out of the ocean, it wouldn't be enough energy to do anything with. Also, then presumably the ocean would be quite chilly. All right, let's talk about thermodynamics. Thermo means heat. Okay. So,
can you go back?
Yes, ma'am. You tell me when you're ready.
You can go.
Okay. Thank you. Thank you for slowing me down. All right. So thermo means heat. So the first law of thermodynamics is going to sound a lot like the law of conservation of mass. Okay. The law of conservation of energy says energy is neither created nor destroyed. Okay. So we are not creating or destroying energy. We're just moving it around, just like mass. So if you can remember the law of conservation of mass, then you've also memorized the first law of thermodynamics. Okay. I usually don't give a lot of essays, but there will be not an essay, but I will basically say, write the first law of thermodynamics, write the second law of thermodynamics, write the law of conservation of mass. So you need to memorize them. Okay. So mass is not created or destroyed. It just changes forms. Okay. And energy is not created or destroyed. It just changes forms. Okay. So now the question is, if you can't create or destroy energy, how are you, where is it going? Okay. Well, I think most of what we know tells us that anything that we use for energy, like light bulbs or car engines, give off heat. So typically, that heat, that energy that is not usable in a system is sent out in heat. So the second law of thermodynamics says energy always goes from more useful to less useful. Okay. So hold on. No. Okay. I'm going to go back. So another way of saying this is entropy. Entropy is disorganization. So I learned the law of thermodynamics being that energy goes from organized to disorganized. Okay. So this says useful to less useful because remember, we learned that the most useful forms of energy are the ones that are the most organized or the most put together. Like the sun is by far the most useful energy source, and it is incredibly useful, but it's also incredibly organized because everything is very small. And then when we disperse that heat from the sun into the ocean, that is less organized. Okay, so I learned that it goes from organized to less organized. But either way, there is absolutely no, so far, and I would love for one of you guys to grow up and invent a 100% efficient machine. In other words, a machine that does not give off any heat and all the energy you put in is used for doing work. Right now, there are no such things. In fact, most of what we use for energy is very inefficient. So, for instance, if you're sitting in a room that has a light on, okay, if you touch that light bulb right now, it's going to be hot. It's going to be hot because light bulbs give off heat while they're also using energy. So again, your car engine is so inefficient, so inefficient. It gives off, not only does it give off heat, it also gives off exhaust, which is incredibly disorganized. Remember, because matter that's disorganized is typically the gas. So it's giving off gas, it's giving off, emissions, which are gases, and it's giving off heat, right? Now, it's the best thing we got going. I mean, we don't have any other real better way to more efficiently use the energy, but this is very typical of the law of the second law of thermodynamics, which is energy goes from more useful to less useful, or from entropy to enthalpy, or enthalpy to entropy, sorry, or organized to disorganized. Okay, the more disorganized, so go back here, the more disorganized the energy is, the less capacity it has, a low capacity to do work because it's dispersed, right? Now, so let's go back to, let's go back to engines here. So one of the ways that the more energy efficient cars work actually don't have anything to do with fixing the engine. They actually, so I don't know how many of you know anything about cars. And before I married my husband, I knew zero things about cars, but the man talks and sometimes I listen. So here's what happens when you push on the brakes, you have two parts of the brake pad that come together. And that friction of those two parts of the brake pad coming together are actually what stops your vehicle. Okay. That what energy efficient cars are doing. So when those two things rub together, that creates friction, which creates heat. So what some of the hybrid cars have done is they have that brake pad when it comes together, they have figured out a way to gather that energy from the friction and use that to power things in the car rather than using gas. So there are other things than just an incredibly efficient engine, although it would be great and you'd be really, really rich if one of you guys figured out how to do that. All right, so systems have inputs and flows. So this is where we're talking about an ecosystem. This is where we get into actual ecology. So a system is a set of components that interact in a regular way. Your body, the earth, the economy. You can even say your biosphere or your biome or even your ecosystem that you live in. So inputs come in from the environment. So in other words, look, if we're thinking about, so this is we always hear about how Kendra works. So Kendra, she makes some money at her job, so that's input, right? Then she's gonna put them in a bank, and the bank is probably, if it's like most banks, it takes out just a little bit, like $1 for every $100 she puts in or something like that. Okay. And then her output is everybody got bills, right? So you got bills you got to pay. And, you might also want to buy some clothes or, get your hair done, something, right? So this is the money coming in. The bank is going to hold it and it takes out a little bit for processing. And then you got your outputs. So inputs, throughputs, and outputs. So in an environment, you have inputs of energy, which is typically the sun. Okay. And you have inputs of matter resources. So, the actual atoms and matter. There are processes. Okay. So, like, in other words, if we want to put the sun's energy in, we're going to use that to create, we're going to do photosynthesis with it. We're going to use it to power the wind. We're going to use it to do a lot of things. So if we're talking about the sun, there's a lot of processes in the environment that involve the sun. But as for every process, we're going to lose some output. So we have work products, we have waste, pollution, heat. Okay. So all of these inputs. So what I need for you to know from here is inputs go into a system, then throughputs are the actual system, and then outputs are the things that go out of the system. Now, every system is going to be different. We're basically going to spend the rest of the year talking about all the different kinds of systems and how they work together and how they are not efficient or they are efficient. Okay. So inputs go in, flows or out or throughputs are basically different system processing, and then outputs to the environment. If we were talking about our human body, an easy one is our digestive system. We put food in, we use it to power our body, we send waste out. We also use it for heat production, right? Our body is constantly producing heat on the inside, but that's an anatomy lesson I'm not getting into. All right. Now, a lot of these systems are going to be in what we call feedback loops. So these system processes, these throughputs, we're going to talk about feedback. So any system is going to be able to provide some kind of way to get the system started again. So in other words, if there is a change and that change causes increase um, an increased change in the same direction. This is a positive feedback loop. So let's go back to our deforestation from, I don't know if you even remember, it was like a week and a half ago. We had two places that we were comparing. Well, let's take the one that had all the trees here and the stream in the middle. Now, if something comes along and for some reason, maybe this water widens this way or something like that, it gets a little bit of decreased vegetation. Okay. What's going to happen is that's going to lead to soil erosion and more nutrient loss, which means we'll have more deforestation, which means more vegetables and or vegetation are going to die, which means more soil erosion. So here we go again, more soil erosion, more deforestation, and this goes on and on and on. Okay, this happens a lot in environmental issues. In the human body, it's really only one feedback loop, and that's giving birth. Because you increase contractions, increase until homeostasis is reached. And homeostasis is not having a baby live inside of you. So that's kind of the only system in the human body that works like this. But environmental problems are very often positive feedback loops because, and it sounds like something good would happen when you think of positive, but positive just means that the changes are growing and getting bigger and then causing more changes, which are getting bigger. So you have soil erosion that leads to nutrient loss, so the plants can't grow. The plants don't grow, so you have more soil erosion, more nutrient loss, so more plants can't grow. And then it just keeps going and going until you have no plants and no soil, essentially. Okay, and that's a positive feedback loop. A negative feedback loop causes the system to change in the opposite direction. And the quintessential or the typical example for this is the thermostat in your house. So the thermostat in our house or this house here is set to 70. Okay. So when the temperature reaches 71, it is going to turn on the air. Okay. The air conditioning. Okay. So when the temperature reaches 71, it's going to turn on the air conditioning. The house goes back to 70 and then it'll turn off, right? Once it reaches 70. Now, if you have the heat on and it goes down to 68, the heat is going to turn on, right? It's going to heat up the house. And then once the house is back at 70, then boom, it turns off. So this is something that's going to turn on and off. Now, this is the most typical way that our body regulates itself. So for instance, when you eat a cupcake, that has a lot of sugar in it. So what happens is your body is going to secrete insulin, which is going to take the sugar out of your blood and store it so that you don't have such high sugar in your blood. But then, of course, you feel guilty about eating a cupcake because that's so much sugar and half your calories for the day or whatever. So then you don't eat for a really long time and your blood, the sugar in your blood gets used up. Well, then your body secretes something called glucagon. And glucagon takes the glycogen that has sugar stored in it, releases that sugar into your bloodstream so that your blood sugar can go back up. So you remain essentially, even though you put in some sugar sometimes and use up sugar sometimes, you still maintain a relatively level blood sugar throughout the day. Okay. So this is not as common in ecosystems. Okay. So we will talk about a few as we go, but this is not nearly as common. So here's one problem with ecosystems, though, is, and I have this problem too. So I have food allergies. And one of the things with food allergies is sometimes your reaction is delayed. So, like, I do have a food allergy, which will immediately make me sick. But some of mine have to go through my digestive tract for a little bit before my system starts to attack it. So it'll be 6, 8, 12 hours after I've eaten something that I feel sick. And so that made it very hard to diagnose the food allergy because it was so much of a distance. I could have eaten, in a 12-hour period, you could eat 50 different things. And so it's hard to pinpoint what it was that actually hurt. And that's also like an ecosystem. So for instance, we have been putting coal and all of this stuff out into the atmosphere for ever since the Industrial Revolution, right? So for almost, I guess the Industrial Revolution was like the 20s. So, I mean, 100 years. And we're just now seeing some of the effects of climate change, right? So it is hard to get a lot of people behind climate change because they're like, well, I mean, so it's only 1 degree. So it happened over 100 years. So, whatever. It's hard for a system. There are a lot of time delays, is my point. And so the time delays, actually make it more difficult for scientists to pinpoint the problem and for the scientists to communicate with the public, hey, this is really the problem. Because they go, oh no, we've had cars for 100 years. That can't possibly be the problem, right? Well, the problem is that we've had cars for 100 years, right? So 100 years of buildup in the environment has wreaked havoc. And there is always a tipping point. And this is what I feel like if you have somebody sitting next to you that's poking you, and if we were in class, I would do this to someone. And, someone says, oh, Miss Klug, can you stop poking me? And then Miss Klug keeps going. Eventually, somebody is going to smack Miss Klug and be like, Miss Klug, I can't take it anymore. Stop it. That's the tipping point. Okay. You reach this level where there is just you've had enough. The system cannot handle it anymore. And the system is going to fight back in some way. So again, with climate change, we've put all of this pollution in the environment. It's actually increased our global temperatures, which means the ice caps are melting. Okay. So eventually it got warm enough to start melting the ice caps. Okay. So eventually that system reached its tipping point. And every person and every system, stop it. I guess you stopped. I'm sorry. Every person and every system has a tipping point, right? You can't abuse a system. You can't abuse your body. Okay. That's another thing. Like I think about, so I was an athlete in high school and college, and I think about all the things that I did to my body, the surgeries and things. And now I'm paying for it, right? Eventually your body is like, you know what? You've abused me long enough. Now I'm going to, make sure that you have plantar fasciitis and Achilles tendonitis and tennis elbow and all this other stuff you never had before, right? Because I've basically hit my body's threshold of, and I've used it a lot, so it gets tired. All right, the last thing we need to talk about is synergistic systems. So this is where, this is all over, okay? A synergistic system says two or more processes combine in such a way that the combined effect is greater than the two separate effects. Okay, so if we're going back to the tapping example. So if, oh wait, no, I don't want to do that. If I don't want to do that. Now I'm stuck. If I am tapping, let's say I'm tapping Kayla, okay? And hold on, let me go all the way back. Let me do that. If I'm tapping Kayla, then I get Christopher in, and we both start annoying her that way, right? And we both start bothering her. She is going to get angry faster than if it's just me, right? But if it's two of us, that's gonna increase her agitation level with us, correct? So synergy is essentially like that combined effect. So it is helpful if you study with a study partner, right? If you two study together, because two heads are better than one. It can be helpful when, if you're trying to clean up a park. It's better to have, several people cleaning up the same park than one person cleaning up three people cleaning up three parks, it's more efficient to have and more useful to have three people cleaning up one park, right? It'll go faster. The other thing happens with smoking. So if you smoke, all right, you're probably going to die of lung cancer. But if you smoke and you eat terribly, that's a recipe for death. If you smoke and you never exercise, death. If you smoke and inhale asbestos particles, you're definitely getting lung cancer. I mean, definitely. So it's a cumulative effect. And in fact, a synergist reaction basically can be called an accumulative energy. Basically, the more that you do something, or the more you have different factors working together, then you're going to have a greater effect. Okay. And so this is really important when we talk about pollution, because typically if I walk outside of my neighborhood or whatever, there are going to be cars that are going to give off pollution, right? There's houses that give off pollution. There's trains that give off noise pollution. And so there are many different types of pollution, and they are essentially interacting in such a way that they're going to have a greater effect than they would if it was just some cars emitting some gas. Okay. All right. So that is all of the notes for this unit, for this chapter. Your assignment for the rest of the class, there is a Bill Nye video. You guys, I love Bill Nye. And the Bill Nye video is actually on Actively Learn. So go to Actively Learn. There is a Bill Nye video, and I would like for you to answer the questions and watch Bill Nye. He's going to talk to you about thermodynamics. Okay. And so if you were here when I took attendance and you have no questions, then please go to Actively Learn and watch your Bill Nye video on thermodynamics.